This is question number 5. The viscosity of liquid can be measured using a rotating cylinder viscometer of the type illustrated in figure 4. In this device, the outer cylinder is fixed. So this is the fixed outer cylinder, and the inner cylinder is rotated with an angular velocity omega. The torque T required to develop omega is measured, and the viscosity is calculated from these two measurements. Develop an equation relating mu, omega, TL, R0 and Ri. So neglect and effects and assume the velocity distribution in the gap is linear. So in this question, we will discuss about the mechanism of rotating cylinder. So we are using this idea to measure the dynamic viscosity. As I said in previous lecture, one of the simple method to measure the dynamic viscosity is by using the rotating viscometer. So and then what you need to understand here is, first, you need to understand how to draw the velocity profile or the velocity distribution. So according to this mechanism, we found that this rotating cylinder is rotated at certain velocity. So means that we need to draw the velocity distribution from the top view here. So and then from the top view, we could find that, so we have a cylinder here. So we have a cylinder here, and then it is covered by an outer cylinder like this, and this cylinder is fixed, okay, but the inside cylinder is rotate, is moving, okay. So and then according to this idea, we could draw the velocity profile. So means that your velocity profile should be like this. So let's say this is the inner cylinder and this is the outer cylinder. So what you need to draw is, you need to first you need to draw, for example, okay, so this is the rotation speed. So mean it's rotate clockwise like this. So and then you draw, we could draw the two molecules that stick on the surface here. So and then here the velocity is 0 because the cylinder is not moving. However, the molecule here, so it stick very hard on the surface, but this object move at certain velocity. So means that we could draw a velocity distribution something like this. So means that if you want to draw here, so let's say the rotational is counterclockwise like this. So means that the velocity triangle or the velocity distribution will become like this, and at the bottom here it should become like this. Okay, I hope you could draw the velocity distribution very well. So and then bear in mind that velocity distribution is represent the linear velocity. So means that the velocity must be draw straight line like this. So please do not draw, for example, if you draw a curved surface here, so please do not draw velocity distribution curve like this. Okay, because the velocity is actually not curved like this one. So you need to draw a straight line here, because the velocity here is actually represent the linear velocity, and it is actually the tangent at this point. So you need to draw a straight line here. So and then we go like this one. For example, we start with a small area of this one. So means that we have a d theta at this area. So and then we have an distance here as an x. So we know that the force is tau times A, and the shear stress is tau mu du dy. So and then we use another equation, because in this situation the cylinder is rotated in rotational velocity. So we use the idea of torque, which is the force times the radius. So, and then because we are focusing on this small area only, so we could say that the small torque here, okay, dq is equal to df times r. So because the small torque here is come from the small force times r. So, and then we could substitute the value of df here according to this equation. So we could write as tau dA times r. So this r is actually the same r here. So, and then we could rearrange the equation, and we could write as dq is equal to tau r and dA. So, and then we need to determine what is the dA. So according to the diagram here, so the dA means the area of this one. So if we draw in 3D, so we only take the small area here, so means that the area of this one, it is actually the area of this one. So we just take the area of this one. So what we need to do is we need to calculate the distance of this one, and then we need to multiply with the height of this one. Okay. So, and then we could calculate it is x times L. So we could calculate the x by using the r d theta, which is theta is in radian, and L is the height of the rotating cylinder. But bear in mind, in this situation, we only need to take the height of a rotating cylinder that give you gap between the gap and filled with liquid. So in this situation, so the air should be from here until the bottom part here. Please do not take the whole area of this one, because in this situation, in this area, there are no liquid fill. So means that the shear stress, okay, is very minimum, because the fluid inside this area is actually an atmospheric gas, atmospheric fluid. So means that the gas will give us very low shear stress. So in this situation, we could neglect the effect of the gas of the atmosphere of the atmospheric. So then we could substitute the value of dA here into this one, and finally we could get the value of dq is equal to tau r r1 d theta and L. So, and then in this situation, previously we have an small r here. So, and then here we have an r1. So please make sure that you really understand the r here is equal to r1, because according to this diagram, the r1 is the radius of the moving cylinder. So how to get the value of total torque? So after we have the equation of torque like this, so we integrate both sides, we integrate left and right. So, and then we could get the integration of dq here will give us the amount of total torque, and the integration towards the d theta here will give us tau r1 square L 2 pi. Because the limit of this integration is from 0 to 2 pi, because our object is in cylinder shape. So means that if we do the calculation, if we do the integration, so we need to calculate along this parameter. So the limit is from 0 to 2 pi. So, and then we substitute the value of tau here with this equation. Tau is equal mu du dy. So and then the problem is, another thing that you should know is, so tau is equal mu du dy. So and then the u here is the linear velocity. So this is the linear velocity. So it means that in our application there are no linear velocity because the cylinder here is rotate at certain RPM. So means the unit of RPM itself not showing the linear velocity. So please make sure you could convert the rotational speed into the linear velocity. So the equation is u is equal to r omega is equal to pi dn over 60. So means the u here is the linear velocity in meter per second unit, and the r here is meter, and the omega here is the radian over second. So and then the pi is constant. You have the diameter here, and then the n here is rpm, mean rotation per minutes. That's why we need to divide with 60 here to make sure the unit is maintained in meter per second. So this is the relationship between u, the linear velocity, with the rotational speed, because sometimes rotational speed will be given in radian per second, and sometimes it will given in rotational per minute. So we substitute the value of du here with r1 omega, and then we substitute the value of dy here with r0 minus r1. So if we know that we have a cylinder here, and this is the outer cylinder, so we have the r1 here, and the outer one is the r0. So the difference of this one will give us the gap between these two surfaces. Okay, so we substitute the value, and then we could get the total torque is equal of this one, mu r1 cube omega L2 pi over r0 minus r1. So how people could determine the value of mu in this calculation? So we know that the torque here can be setting in the device. So and then the r is the constant we could measure from the device. So and then the rotational speed can be measured, the L and 2 pi can be measured, and the gap is also can be measured. So means that the only unknown parameter is actually the value of mu, which is the dynamic viscosity. Okay, so means that if we could set the value of torque here from the machine, so and then we could calibrate the viscosity, so means that we could measure the value of mu by using the rotational viscometer. Okay, now I would like to share you a simple step to solve this problem. So why? Because if we see our application is rotational cylinder, so we have a cylinder here. Okay, we have a cylinder here, and then if this cylinder rotate at certain speed, let's say we have 2 points here, one point at the top and one point at the bottom. So we found that these 2 points will travel with the same distance. Okay, so why it is important? Because you know that the force is actually tau times dA. So the A here is fixed, means there are no changes between point upper point and lower point. So means that actually it is not compulsory for us to do the derivation like this one. So because there are no changes, there are no different for at all the point. So what we could do is we just use these 3 equations to solve the problem. So we have torque is equal to Fr force is equal to tau A and tau is equal to mu du dy. So and then we substitute the force here with tau A, and then we substitute the tau here with the mu du dy. So we get the value of this one. So and then we change the amount of u here from the rotational speed into the linear velocity. So we could get r1 omega here, and then we substitute the value of dy here is the gap between the moving and fixed surface. So it is r0 minus r1. So and then we substitute the value of a here as 2 pi r1 L. So and then the value of r here is r1. So and then finally we could get the final answer similar with our derivation method here. Okay, so it is q is equal mu r1 cube omega L 2 pi over r0 over r1 over r0 minus r1.